Hello everyone, so this is a new topic, electrophilic aromatic substitution, and I will start with the Arenium ion mechanism and the energy profile diagram. So aromatic substitution, it can be two types. One is electrophilic substitution, another one is nucleophilic substitution. So the incoming species with which you are attacking the aromatic molecule, mostly benzene or benzene derivatives, it may be an electrophile or it may be a nucleophile. So electrophile means which is electron deprived species. It is searching for some electron density, electron rich region. But nucleophile is already a electron rich species. So obviously it will search for some electron deprived region. Fine. But in case of aromatic substitution, normally it is common, that is electrophilic substitution, that is the most common, not nucleophile. Nucleophilic substitution, though there are many examples of nucleophilic substitution, but if you compare the number of electrophilic substitution with nucleophilic substitution, obviously the number of electrophilic substitution, it is more compared to nucleophilic substitution. But what is the reason? That we have to know. Now if you look at the pi electron density of benzene ring, here we have taken simple benzene ring because that will be convenient to understand. So there is pi electron cloud below and in the lower region of the sigma skeleton. So what is sigma skeleton? The sigma skeleton is the 6-membered ring which is formed by 6 carbon. So this is the sigma skeleton. Below and in the lower region there is pi electron cloud, and pi electron clouds are loosely held if you compare with sigma electrons. So if it is loosely held, obviously it will be easily available electron source. So if it is electrophilic substitution, then suppose E plus, that is our electrophile, and if it is nucleophilic substitution, then this is the species, Nu minus. So obviously if a negatively charged species, if it is coming towards this already loosely held pi electron, there will be some repulsion. So it will repel a negatively charged species or neutral nucleophile. Suppose if the nucleophile is neutral, then also there may be some lone pair of electron. Okay, so not only always that the nucleophile it will carry some charge, plus though still there may be some lone pair of electron. That can also be neutral electrophile. But in both cases there will be repulsion between these two negative charge. So that is the reason that electrophilic substitution is more common. The pi electron cloud, it will attract it towards this E plus, and then there will be a bond formation, carbon and electrophile, bond between carbon and electrophile. And finally this carbon hydrogen bond will be broken and the aromaticity will be regained. Okay, so this CH hydrogen, that is replaced by E. Okay, so this is our final product. Now, what is the mechanism of electrophilic substitution? Actually, there are two steps. The first step you can see here, we have taken a benzene derivative. Now, why I have written in this way? Because Y may be at any position. That is compared to the position of E, it may be at any position. So that is why it is written in this way. Now, E plus is our electrophile. Now the attacking electrophile, it may be a positive ion that is carrying positive charge. It may be a positive end of a dipole. Suppose you are using some molecule XY, and X, that is the side of X, that is positive side, and the side of Y, that is negative side. So from the side of X also, that is the positive end of a dipole, that can also act as electrophile. Or it may be some induced dipole, that is partial positive charge over X and partial negative charge over Y. So different types of electrophile may be there, but here we have taken E plus. So the first step is the electron density over the benzene ring. It will attack this E plus and there will be formation of Ce bond. So this step you can easily understand that the aromaticity is lost. 4n plus 2, this pi electron, here 4n plus 2, n is 1, so the number is 6. So that electron 4n plus 2, that will not be maintained. So aromaticity is lost. So this step is slow step. But the second step, this is very fast. Why? Because aromaticity is now again generated. So this CH bond, it will be now broken. And finally, we are getting E substituted product. Though we do, as Y, we do not know what is the exact position of Y with respect to E, and how the position of electrophile with respect to the position of Y, that is, it is determined, that will be discussed later. Fine. So the intermediate that you can see here in between the two steps, that is known as Arenium ion. There are some also name you can use, which is benzonium ion, sigma complex, or well and intermediate. Any of this name you can find in books. Fine. The leaving group mostly H+. So why we are calling it leaving group? Because from the intermediate this CH bond that is broken, so hydrogen is leaving. Okay. So Lg mostly H+, it must depart without its electron. So that is why it is proton, H+. And the proton is removed by the anionic part of the sigma complex. Though here the anionic part is not mentioned. When we will discuss actual examples, then you will understand it, that there is a anionic part. So that anionic part, that will capture this proton, that will help to deprotonate and to regenerate the aromaticity. The reaction is influenced by other groups that are present on benzene ring. So here you can see in the benzene ring, there is a presence of the group Y. Okay, so depending on the nature of Y, the reaction rate may be influenced, and also the position of E. Okay, that is the orientation of E, that will also be determined. So here we have written all the resonance structures of this Arenium ion. You can write Y in this way. So the positive charge, this double bond, if it is shifted here, now the positive charge, it will be at this carbon. In the next structure, positive charge is at this carbon. So basically you can see with respect to this carbon positions, if you consider this carbon as 2, this carbon as 4, and this carbon as 6. So 2, 4, 6, these three positions, there is actually positive charge generation. So if we draw the average structure with the partial positive charge, this will be the nature. So carbocationic character, it will be at ortho position. Ortho position means the 2 and 6 position, and para position, that is 4. But never you will find it at meta position, that is these two carbon, that is 3 and 5. Okay. Now as I have said that the electrophile, it may not be always the free positively charged species. The attacking electrophile may be a molecule also instead of ion. So suppose XZ, so X side, that is the positive end, Z side, that is the negative end. So in this way also we can get our electrophilic aromatic substitution. Next we have a question that typical reactions of alkene, mostly it is observed that it is electrophilic addition reactions. But typical reactions of benzene ring or any benzene derivative, that is mostly electrophilic substitution, not addition. So what is the reason behind that? So here we have taken a general alkene structure. This is our electrophile. Now if when the double bond, that is a pi electron, it is attacking the E+, and we are getting a carbocation here. Now the nucleophile, actually you can consider the electrophile in this way, because obviously the positively charged species, that will be connected with some negatively charged species. So suppose this is a molecule and first E+ is attacking, and nu-, that is the nucleophile, that is already in the reaction medium. Now this nucleophile, it can attack here. So if that is the case, you are getting substitution product. Sorry, this will be substitution and this will be addition reaction. Sorry for the mistake. So if the nucleophile is attacking at the positively charged carbon, you are getting substitution product. But suppose if this hydrogen is captured by the nucleophile, then you will get the double bond again. So now you are getting substituted product. sorry, actually it is right. I have done the mistake. Okay. Yes, the first product is addition product. That is double bond is not present and it is now sp3 carbon. From sp2 now we are getting sp3 carbon. But the second product is substitution product. Okay, that is this one. So here one of the hydrogen that is substituted by E. So why addition products we are getting mostly from alkenes? The reason is the sequence of addition is thermodynamically more favorable, that is exothermic, than the sequence of substitution. So that is why substitution is not so common, but addition is common. Okay. So the reason is why we are saying that it is thermodynamically more favorable. The reason is the energy which is required to break this pi bond and also to break this Nu, or you can say to generate the electrophile, that energy is less than the bond formation of this Ce and Cnu. So that is the reason that it is exothermic. So the sequence of addition is thermodynamically more favorable than the sequence of substitution, and that is the reason that typical reactions of alkenes are electrophilic addition reactions. But what about the benzene ring? In case of benzene, if now we are using electrophile again, when the electrophile, the that is the pi electron, it will attack the E plus, there will be a positive charge generation. Now the nucleophilic part, what it can do, it can attack at this position. So in that case, you will get addition product. Okay, but in addition product you can see your aromaticity, it is no longer present. It is removed. Fine, which is energetically very unfavorable. But if it is nucleophile, then the hydrogen at this position, that will be removed by this negative end, and as a result you will get aromaticity regeneration. So that is the reason that sequence of substitution is thermodynamically more favorable than the sequence of addition in case of benzene ring or its derivatives. Fine. Next we will see the energy profile diagram, but before that, look at these two species. This is our Y substituted benzene derivative and electrophile E plus. Now there may be different types of electrophile. If the electrophile is Cl plus, you will get chlorination reaction. If it is SO3H, it is sulfonation. If it is any alkyl group plus, R plus, then you will get Friedel-Crafts alkylation. If it is RCO plus, you will get Friedel-Crafts acylation. In this way, depending on the nature of the electrophile, there are different types of electrophilic aromatic substitution. Okay, and as we have said that the positive charge generation, that will be at the ortho, meta and para. Okay, now if it is ortho attack, that will be the attack at these two positions. These two positions are ortho, that is 2 and 6. If it is meta attack, then these two are the positions 3 and 5. If it is para attack, that is the electrophile is now attached to 4 carbon, so there is only one para position. Obviously meta positions with respect to Y, these two positions are equivalent, so at any point it can attack, and if it is ortho attack, these two positions are also equivalent. Okay, now come to the energy profile diagram. As we have said that the first step is slow step and the second step is fast step. So obviously the activation energy for the first step, that is the activation energy which is required for this Arenium intermediate generation, that energy is very high because this intermediate there is no aromaticity. So obviously from an aromatic molecule you are making non-aromatic molecule, obviously it will need some energy. So that is why the first step is slow. So daily 1, that is greater than daily 2. This energy is very low, that is lesser compared to the first one. So that is the reason the second step is fast. First step is slow. Okay. Now see this energy profile diagram that we have just seen here. If we elaborate this energy profile diagram, you can get something else. So this is energy diagram for sigma and pi complex. So this is the detailed discussion of the sigma complex, how we are getting it. So this is our benzene ring, this is the electrophile. So in the first step, there will be weak interaction between this pi electron and the E plus. So here you can see this is pi complex and this is pi complex number 1. So there is just the interaction which is just started. It is not, that is the E, it is still carrying the positive charge and no covalent bond is formed yet. Fine. Next what will happen? The actual sigma complex, that is our Arenium complex that we have already seen, that complex will be formed, and here you can see the actual covalent bond between the carbon and the electrophile, now that is formed. Fine. So in the next step, though we know this is the final product, actually we have omitted these two species in the previous mechanism, that is the pi complex 1 and pi complex 2. But and if you just omit these two species, it will be the step like this. This is the first step, this is the second step. But if you include these two pi complex 1 and pi complex 2, then it will give you the detailed idea. Okay, so in the next step of sigma complex, here you can see the next step is actually the breaking of this CH bond. So now what is happening, this H plus, it is now free, but still there is a weak interaction between the pi electron and the H plus. Okay, it is not fully free from the benzene ring, but finally now it is completely departed. Okay, so if we draw the energy profile diagram for this detailed mechanism, it will be like this. Okay, see. So this pi complex 1, this if you call it as intermediate, suppose this is the intermediate and this is our actual Arenium ion intermediate. Okay, so this is the sigma complex and pi complex 2, that is this one. So this is the activation energy for the formation of pi 1 complex. This is the activation energy for the formation of sigma, which you can understand it is higher than the previous activation energy, and this is for the pi 2. Okay. So available data suggests that in most of the electrophilic aromatic substitution, in short we call it EAS, the high energy transition state, it strongly resembles the sigma complex. So this is the high energy transition state. So suppose I am putting a star mark here, and now I am going again back to our original energy profile diagram. So that star mark position is actually this position, right? So actually what we have done, we have elaborated this portion in the second slide. That is the difference. Okay, though most of the time you will see only this energy profile diagram, but before formation of sigma complex there is formation of weak pi complex also, and after the sigma complex, when it is broken, there is also the formation of pi complex 2. Okay, so that is the energy diagram of sigma and pi complex. Next we have to know, though we are saying that Arenium complex is formed, it is the intermediate, but what is the deep evidence behind this formation of Arenium ion or sigma complex, whatever you say. So we have to find the evidence behind stepwise mechanism. Basically it is the evidence behind the Arenium ion formation. So if we can somehow isolate the Arenium ion, which is actually done by Dr. Ola using NMR spectroscopy, actually he has found it for the first time. So here you can see our starting material is mesitylene, 3-methyl group substituted benzene ring. We are using ethyl fluoride, BF3, and very low temperature, -80 degrees centigrade, because we want to isolate the Arenium ion, and for that obviously you have to lower the energy because it is very unstable. Okay, so temperature should be very low. Now ET is attached here. ET is actually our electrophile, ET plus, and BF4 minus, that is a negative counterpart, and finally this CH bond will be broken and this is the product. But this intermediate, it is actually isolated. And not only this molecule, in a large number of cases, that is the sigma complex intermediate, they have been detected. Okay, and in some cases that is they have been isolated also as salt. So you can easily understand this is a salt because BF4 minus, that is the counterpart here. So this is a positive counterpart, this is a negative counterpart. So this is acting like a salt. So in some cases it is detected in the reaction medium. In some cases they have been actually isolated as salt. Now you can say that this is mesitylene, that is benzene ring, and 3 methyl substituents are there. So that is why these 3 electron donating substituents, it is making this positively charged species stable. But actually, if you consider simple benzene ring where no substituents are present, that is the simplest benzonium ion or arenium ion that is possible, that also prepared and studied, that also can be prepared and studied under favorable conditions. If favorable conditions are provided, then this can also be studied. So it is a very significant evidence that stepwise mechanism is going on, because if there is no stepwise mechanism, then this type of salt detection or salt isolation, that will not be possible. Okay, so this is the first evidence, and now come to the second evidence. The second evidence is regarding isotope effect. But first you have to know what is primary kinetic isotope effect. So this is the change in rate due to isotopic substitution at a site of bond making or breaking in the RDS state. So suppose in your compound there is a CH bond, okay, and now the rate constant for the reaction is KH, and you want to determine, you want to identify whether this CH bond breaking it is taking place in the RDS step or not, that is rate determining step. So for that purpose, what we will do, we will change the hydrogen with its isotope deuterium. So CH bond breaking energy and CD bond breaking energy obviously not same. To break the CD bond, we require more energy. So now the new rate constant that you will get, if CH or CD bond formation it is involved in RDS, obviously KD now it will be less. So if CH or CD bond formation it is not taking place in the RDS, then the ratio of KH by KD, there will be no change, so it will be 1. So if by doing this kinetic isotope effect experiment, if you find that KH by KD it is 1, it means that there is no primary kinetic isotope effect. But if it is more than 1, then we have to say yes, there is some effect. Okay, so basically in the mechanism that we have seen, the first step is the attack of the pi electron cloud of benzene ring to the electrophile, and in the second step, that is the first step, there is removal of the proton, that is the breaking of CH bond. So obviously CH bond cleavage, that is not happening in the RDS step, so we should get KH by KD this value as 1, right? So if the hydrogen departs before the arrival of electrophile, suppose the mechanism that we have already seen, that is not taking place. Suppose CH bond breaking is taking place fast. So that is one possibility. Another possibility is arrival and the departure, that is arrival of the electrophile, departure of the hydrogen, both are taking place simultaneously. So these two are the processes. So if that is the case, there should be a significant isotope effect. KH by KD should not be 1. But many studies have been carried out. In most cases, especially in case of nitration, it was found that there is no isotope effect. So it means that KH by KD, it is 1. So if you take, for example, nitration of benzene and nitration of C6D6, that is the corresponding deuterated version of benzene, both were found to occur at almost equal rate. Okay, this reaction, this is benzene, but suppose if you are changing all the 6 hydrogens by 6 deuterium, then also the rate is same, equal rate. So that means KH by KD is 1 and there is no isotope effect. So the slow step, that is the rate determining step, it is actually the attack of the pi electron cloud to the electrophile. So there will be carbon electrophile bond formation, not carbon hydrogen bond cleavage. Okay. So that is all about isotope effect. Though we are saying that many studies have been carried out and isotope effect not found, but I should also mention here that in some instances isotope effects have been found. Very rare. But the values are generally much lower than expected for either the AC1 or the simultaneous mechanism. So AC1 mechanism is the opposite mechanism. Suppose where the CH bond breaking is taking place in the RDS and then it is attacking the electrophile. Okay, but that is not actually taking place. So this is one possibility. Another possibility is simultaneous mechanism. So though in many cases isotope effects have been found, that is, it is not, the ratio is not 1, it is greater than 1. But the values that you should expect from the opposite mechanism, that is the reverse mechanism or the simultaneous mechanism, still the value is very low than that. So there must be some another explanation for that, that why that is the actual theoretical kh by kd it should be 1, but still we are not getting that. There must be some other explanation. But remember, for this mechanism, that is the reverse mechanism, and for simultaneous mechanism, suppose kh by kd, I am just saying as just for example, suppose the value should be 5 to 6 kh by kd, but actually it is much lower than that. Though it is not equal to 1, but still it is not so high as this. Maybe it is 2 to 3. Just for example I am saying. Okay. So this is the second evidence of stepwise mechanism. So it proves that Arenium ion is formed as intermediate. So this is the first video of electrophilic aromatic substitution. In the next video I will come with how we can generate the electrophiles and also the orientation of the incoming electrophile, and activating groups and deactivating groups. All this we will discuss in the next video. Until then, goodbye. And if you find this video helpful, please like, share and subscribe. Thank you for your time.